Okay, Doki. Today we're doing 6.2 day 1. I will not be going through the whole unit today. I will not be going through the whole section today, unlike I did yesterday. Today I'll be just doing 6-2. What am I saying? I'm doing 6.2. Still on the packet, so I don't have to write everything out. Convenient for me. So we have some definitions and a theorem on this page. We gotta do the definitions first in order to know what the theorem is. We may or may not be doing an activity in class about this. We shall see. Concurrent lines. When 3 or more lines rays or segments intersect at the same point. Awesome. That's concurrent lines. So when we have 3 lines that intersect, 3 lines, rays, or segments that intersect at the same point, those lines are called concurrent lines. The point in which they intersect is called the point of concurrency. So it is the point of intersection of those lines, rays, and segments. So when these concurrent lines all intersect at that same point, this point is called the point of concurrency. In a triangle, the 3 perpendicular bisectors are concurrent. This will make sense when we look at the theorem. And the point of concurrency is the circumcenter of the triangle. Take note of circumcenter. This is the main topic of today. This is what we're focusing on this first day of 6.2 is called, we're focusing on the circumcenter itself. That's what we're focusing on, the circumcenter. So we have a theorem that goes along with the circumcenter. It's called the circumcenter theorem. Oh, funny enough, it works with that. Haha. What does this theorem state? The circumcenter P. Where am I writing this? Oh, I'm like looking way down. I need to write the actual theorem first. I'm looking at my notes and I'm like, what am I supposed to write right now? I'm thinking too far ahead. All right. The theorem that is stated. We have that the circumcenter of a triangle is, I'm good at different color. I'll use orange. I'll copy what's in my notes. It is equidistant from the vertices of the triangle. All right. So we are going to write out the if-then statement. That is what's going to help you actually understand what the heck is being talked about in this figure, because I know there's a lot going on. So you need to write out this statement. Like I might walk around and like check everyone at that point, but like you need to write this out. You need to actually know what this whole like first half is talking about. So in order for this circumcenter theorem to happen, we need to have this if be confirmed. So if we have that the segment PD, PE, and PF be perpendicular bisectors, then that means PC is equal to PB, and that is equal to PA. All right. Got that handled for a second? All right. Let's color. Maybe write it down like if blue, then green or something. So if we have some perpendicular bisectors right here, and if they all intersect at a concurrent point, and that's going to be P. They all intersect. These perpendicular bisectors all intersect at P. So to get this perpendicular bisector, remember, it cuts through the midpoint of each segment. So we have a perpendicular bisector for each side of the triangle. Like I have one for AB, that being at point D. Have one for BC, the midpoint is E. Have a midpoint for AC, that is F. They all have perpendicular bisectors. They all extend and intersect at each other. And they all intersect at P, which is why we have PD, PE, and PF being the segments that we need. If all of these intersect at the same point, or they intersect and meet at the same point, and if they're perpendicular bisectors, that means that PA, PB, and PC are going to have the same length. So adding more congruent marks, this would be our fourth set of congruent marks. We can have that. So if the blue happens, if this is true, if they're perpendicular bisectors, this is true. Then PC is equal to PB, which is equal to PA. Cool. So the circumcenter of P is equidistant from the three vertices. So P is the center of a circle that passes through all three vertices. I'm realizing now that I don't have the picture I put onto this for this part. Like current time, I'm realizing that. And all of you guys don't have it either. So I'm busting out the sheet of paper. I have to like eyeball this now. All right. We're going to follow this. Right on a separate paper. How do we spell separate? That's close enough. Again, this is, you need this. Not that you need it, but it's going to be helpful. We have something like this later in the packet. Kind of. Yeah, we do. Either way. I'm going to take my handy dandy paper. And we're going to draw some triangles. Because the location of this circumcenter P, where these intersect, is different on the different kinds of triangles. Remember that we have three types of triangles. Those being acute, right triangles, and obtuse. I'm going to try my best to sketch this out nicely-ish. That's going to be my acute let's say this is my right. And I will have an obtuse right here. Okay, let's try my best to freeball this, freehand it, and go for it. So, on these different types of triangles, P can be in 3 different spots. It will be not the same spot, but it will be in the same general realm of where P would be. And P would be in these locations. So, on an acute triangle, P, where the perpendicular sides, the perpendicular bisectors intersect, that point P will be inside the triangle. So, if you were, and again, I'm very much free sketching this. You have one right here, one right here, one right here. They intersect and they form their intersection on right here. That's where that intersection is. All right, go to the right triangle. P is on the actual triangle itself. So P is on a side of the triangle. So if I were to draw this, perpendicular, perpendicular, and that would be perpendicular as well. But it's also already there. Like it's actually on that point where it's perpendicular. So P is already right there. It's on the side, on the edge. All right. I put P in the wrong spot, I think. I think I, in fact, did put P in the wrong spot for the obtuse angle. I need to put it downwards. Scribble that out. P is like down here somewhere. All right. Again, very much free sketching this. If we extend our bisector outwards from our figure, then we would see this intersection happen. There we go. P is intersecting outside. Like we have our intersection outside of the triangle. So P is outside of the triangle. Keep this in mind. So P for an acute triangle is going to be inside. For a right triangle, P is going to be on that triangle itself. And for an obtuse triangle, P is going to be outside of that triangle. And this is for circumcenters. Circumcenters, which is made by the intersection point of all of the perpendicular bisectors on these triangles. And each side has its own perpendicular bisector. Triangle. I guess make a note right here. Each side has a perpendicular bisector. And the point of concurrency is the circumcenter of the triangle. I'm just kind of going through and seeing if I need anything else at this point. All right. Maybe note like easy tutorial on getting the circumcenter. Skipping this for a second. We will do example 1, but I need to take a note. We gotta flip the page anyways. Tiny note. Perpendicular bisectors of each side intersect. creates circumcenter length from angles are the same. Yeah, it works. Kind of works. Either way, this, once we put it into practice, will be easy. Like with example 1. I did not get to put this on the nice page. But we're going to find the coordinates of the circumcenter itself of triangle ABC. I guess I'll flip. I have my notes right beside me. I could do it. But we're going to find the points of the triangle. And the circumcenter of the triangle with the coordinates of A being, what is it? 0, 3. B being 0, -1, and C being 6, -1. I'm going to plot it on my graph. There's 3 steps for this problem. Step 1. Graph it. Graph the triangle ABC. So 0, 3. There's A. 0, -1. That's B. And then 1, 2, 3, 4, 5, 6, -1 is C. All right. It's important you actually have to graph this one. You will need it for your actual picture. Okie dokie. So that's step 1. I still need blue. Cool, we did it. Step 2. Find 2 perpendicular bisectors. Which means we need to find right angles. That is the goal of us to do. Goal for us to find something. Anyways, this we need to kind of break down into a few steps. First part, we need to find the midpoint of 2 sides. And then 2, we need to go perpendicular with their slopes. All right. That was such a that's so weird. Why did you say it like that? All right, gonna take a quick note. Pick the easy sides. Like, maybe the sides that have a slope. Like, slope is either 0 or undefined. Like, those kind of easy ones. Like, it needs to be vertical or horizontal. Those ones were gonna help you. Maybe note that as well. Horizontal or vertical lines. That's going to help you. And luckily enough, we have a horizontal and a vertical line. So, ooh, perfect. All right. So, let's get started. I'm going to find the midpoint, and this is why graphing is important, because I don't have to do the equation. I could just count to the midpoint. Like with BC, it's 6 long. That's my midpoint right here. So that is what? 1, 2, 3. 3, -1. Cool. And I'll wait a second. I'm not gonna go further first. We gotta actually do this. So we have 3, -1, and we have, on this one, we will be having, what is that, 1, 1. All right. Oh, that showed up so bad. I might just break out a Sharpie or something. That showed up a little better. 1, 1, 3, -1. That's what we had. Or that's the midpoints of our 2 easy lines. All right. That was step 1. Step 2 is to go perpendicular to those slopes. So right now, if we look at BC, it is going horizontal. At this midpoint is where I'm going to add in that perpendicular slope because it's in the middle. We're basically adding a perpendicular bisector. So just go straight up. If we're going horizontal to make that perpendicular slope, go straight up, go vertical. And then for the horizontal one, as we see, 1, 1, it's going straight up and down with this AB line. Go horizontal with it. There we go. We got our perpendicular slopes now. And then step 3. It is to find that intersection. Find the intersection of the bisectors. So seeing where they cross, that is at 1. Nope, that's at 3, 1. So my final answer is going to be 3, 1 is the circumcenter. Luckily enough, we have another example to go through, so it's okay. So again, I guess break it down. I graphed this. Easy. Step 2 is the hard part. We need to find the midpoints. I found the midpoints for the easy sections being the horizontal and vertical line. You will only be dealing with right triangles for these, I believe. Don't quote me on it, but I'm pretty sure you're just dealing with right triangles for these kind of problems. So you'll always have a vertical and a horizontal line to work with. So finding the midpoint from there, you can either count or do the midpoint formula itself. And then you can go vertical. You just need to change its orientation. So on BC, it was going horizontal. It was going this way. The perpendicular slope would be up and down now. And it comes out of that midpoint because it's a perpendicular bisector. And then you do the same thing for a vertical line. Like if this is my line I'm working with, AB, it's vertical. At that midpoint 1, 1, I go horizontal. That's perpendicular. And then I'd find the intersection between those 2 lines, that being 3, 1. And there you go. This is a right triangle, by the way. If you can't tell, that circumcenter is on that side. So we have another example for this, like in example 2. We're going to find the coordinates of the circumcenter of our ST with the vertices of -2, 5. So 1, 2, 3, 4, 5. That's R. We'll have -6, 5. So 1, 2, 3, 4, 5, 6, 5. That's S. And then T of -2, -1. So we're going to do the same thing, and I'm going to explain it the same way. So we graphed step 1. Step 1 is done. Step 2. And I guess I'll write it out this time, like write out my midpoints and then work it. I didn't really do that with this. I'll do it this time. So let's find out what's vertical, find out what's horizontal. I guess I'll go vertical first. RT is vertical. I guess I'm going to work with that first. So my midpoint for RT, I can count my way to it. So 1, 2, 3. and 1, 2, 3. This is my midpoint. That midpoint looks like negative 2, 2. That's one of my midpoints. I guess I'll find the bisector right now. So to find a bisector going this way, remember we're going vertical right now, so I need to go horizontal from this midpoint itself. So we'd go this way for that midpoint. And it looks to be on y equals 2. Because all of these values on this line will be a y equal 2. So your perpendicular bisector, that actual equation would be y equals 2. And that's all you need to do with that one. Let's go to SR because that's the other like easy side to pick from. Counting what I have, going 1, 2, 1, 2. This is my midpoint here. And that is at, I believe, negative 4, 5. So at negative 4, 5 is where we have our second midpoint. And getting the actual equation for it, or like the bisector. Since we're going horizontal with SR, my bisector is going to go vertical. So moving it up and down. Like so. And now I have my bisectors for each one. Also, what this bisector would be. Since I'm going up and down, all of the y values are going to... No, all of the x values are going to be the same. All the y values are changing. If all the x values are the same, that means I have an equation of x equals and then whatever x value I am working on. So in this case, it'd be x equals negative 4. And now I just need to find that intersection point for step 3. So I'm going to mark that as a check mark, saying that I did it. So step 3, I need to find that intersection. Now this is the case of I didn't draw nicely because that doesn't go on my line, but that, it's not even open. This is my intersection point, wherever that is. And it looks to be at negative 4, 2, being my circumcenter. So, to recap on this kind of problem, all you need to do is to take note of what sides are the easiest to pick from. Those being horizontal or vertical lines, because that's what I did all my work on. I'm like 90% sure most case scenarios you're going to be working with those kind of angles. If not, it's not too... If there is a problem that doesn't become a right triangle that doesn't have these nice lines, I will do it in class with you guys. Like I will stop class and do it so you can see it, so that I'm not throwing you out to the wolves. But you can find the slopes of these lines, and you can find the actual slope by doing the slope formula and then doing the opposite reciprocal to get that perpendicular slope and then actually graph that line. You could, but I don't think you're going to need that at all. If you do, I will say something about it and I'll stop class, but I think you'll be okay. You should have enough practice for this on your homework, and good luck. I don't think it's too bad. I think you'll be okay.